I'm Tom Jupil. Let's try this again. I'm Tom Jupil, the administrator and moderator of Chromatography Forum. Over the past several months, there have been a number of posts dealing with questions about pH and reverse phase chromatography. And so what I've done here is pulled sort of an outtake from our HPLC Basics Equipment and Troubleshooting course that provides a basic overview of how pH works and what the influence of pH on retention in reverse phase chromatography is going to be. So I'm going to start by shutting off the webcam because I'm not sure that it provides any real useful input here. Basically what we're going to do is start off with sort of, as I said, Chromatography 101. And what we're going to look at really as a poster child for this is a weak acid. That's going to be our starting point. And as a weak acid, that means that there's a dissociation involved that looks something like this. Okay, so we have the free acid over on the left-hand side here, and that's going to be in equilibrium with the ionized anion form over here on the right. Now we know that this equilibrium is going to be pH dependent. And if you go to low pH, of course, what you're doing is you're adding hydronium ion, and the law of mass action is going to kick the equilibrium over to the left. So what we expect to have happen is that the free acid here is going to predominate at low pH, and we expect that the anion form is going to be the dominant form at high pH. Now, if we're talking about reverse phase, retention is based primarily on hydrophobicity. Like dissolves like sticks to like. And so we need to consider the hydrophobicity or relative hydrophobicity of these two species. Now, Chemistry 101 says if I have two possible forms, one neutral and one charged, it's very likely that the neutral charge is going to be more hydrophobic. It's going to be greasy, it's going to be organic soluble, however you want to interpret that. And in contrast, the ionized form is going to be hydrophilic. It's going to be more water soluble, if you will. Well, this is the basic information that I need because what I want to be able to do here is to sketch the relationship between retention on the y-axis and pH on the x-axis. So we're going to use K prime as our measure of retention here, and we're going to plot that as a function of pH. We're going to start off at low pH, so we're going to start off down here somewhere. And of course, at low pH, what we have is the free acid. The free acid is hydrophobic, and we know that hydrophobic things are strongly retained in reverse phase, so that suggests that we're going to have a fairly high K prime here. If we kick the pH over to the high side, we're going to shift the equilibrium so that the anion form will predominate, and we expect the anion form is going to be much more hydrophilic and therefore much more weakly retained. And so we're going to be down there someplace. And the question before the house is, what has to happen in between? Well, I can sketch in my sort of best freehand curve here, and I'll confess up front that my artistic skills are fairly limited, but that's just a freehand sketch, and you sort of best smooth curve is going to give you a sort of sigmoid S-shaped plot there. Well, anytime you see an S-shaped plot as a function of pH, the first thing that comes to my mind is titration curve. And really, that's pretty much what that is. If you consider the midpoint of that, the pH at which that occurs is going to be what we think of as the pKa of that analyte. And that's the pH at which the analyte behaves as though it's 50% ionized, or is ionized 50% of the time. And what you expect to have happen then is as you change the pH, of course, the degree of ionization is going to change. Now, pH is a logarithmic function. That means that a 1 pH unit change is a 10-fold change in the concentration of hydronium, to be specific. And so if you go 1 pH unit on either side of the pKa, what that's going to do is it's going to take you from 10% ionized to 90% ionized. And if you go 2 pH units on either side of the pKa, that's going to take you from 1% ionized to 99% ionized. And of course, once you're out beyond 2 pH units on either side of the pKa, the curve is essentially flat and there's very little additional change. So what we expect to see when we look at retention as a function of pH is the effect is going to be most pronounced at the pKa. We're going to see the steepest change. Once you get 1.5 to 2 pH units away from the pKa, things flatten out, and then pH has really very little additional effect. Now that's for a weak acid. Okay, what about a weak base? Well, I'm not going to go through the whole argument again, but basically logic says this is just going to be the same argument, but we're going to mirror image the curve. So again, you're going to have a pKa, but now the high ionization and low ionization sides really flip places. So that's our Boy Scout merit badge approximation or estimate about what's going to happen as we change pH. Well, does this reflect reality? Well, we have some evidence for that. What I've got here is, in fact, retention plots for a mixture of compounds. We've got salicylic acid, which is a strong acid. We have phenobarbital, which is a weak acid. Phenacetin, which is essentially neutral, under these conditions anyway. Nicotine is a weak base, and methamphetamine is a strong base. Well, let's take a look. We're looking at retention volume. That, of course, would be retention time multiplied by flow rate as a function of pH. And peak number 1, which is salicylic acid here, you see really fairly weakly retained. And as we drop the pH now to start coming closer to its pKa, we find that retention increases. And I could fantasize that it does something like that. I'm strictly guessing, okay, as to what's going on there. Phenobarbital, peak number 2, is a weak acid. That simply means it has a high pKa, and what we find here is we're below the pKa, and the retention stays fairly constant, and then as we raise the pH to start to approach the pKa, we see retention decreases. And again, playing fantasy games, it might do something like that. Phenacetin, neutral, doesn't change very much at all in here. Nicotine is the weak base. That's the one where we see most clearly both sides of the curve here. So you see it rises, changes fairly steeply, and then levels off up here. And then methamphetamine, which is our strong base, high pKa, just basically increases and probably levels off at high pH somewhere up to the north of the screen here. So you see that at least for this kind of a mixture of cats and dogs, my Boy Scout merit badge estimate about what's going to happen as a function of pH actually holds pretty well. Now, the implications of this for the chromatography are interesting, because what would happen if we were to run this separation at pH 3? What would be the order of elution? Well, the first peak to come off is number 4, followed by number 5, followed by number 2, and followed by 1 and 3. What about pH 5? Well, if we were to run the separation at pH 5, it would be 1, 4, 5, 2, 3. 1, 4, 5, 2, 3. And if we were to do the separation at pH 7, this one I know, 1, 2, 3, 4, 5. What order would you like your peaks in, ma'am? And would you like fries with that? Okay, so we could pretty much have this our way. Now, granted, this kind of mixture of cats and dogs is not something that you're likely to encounter in the real world. But the fact is that even for samples that have more similar pKa's, we see that pH can have a significant effect on retention and on selectivity, particularly as we get near the pKa. As you get away from the pKa, the effect becomes less pronounced, and once you're more than 2 pH units away from the pKa, the effect of pH becomes essentially negligible.